Folks, in the last videos, we were talking about the reactions of alcohols and all about the surface of a nucleophile, and that was that beautiful OH group that's on the molecule. So let's do a few more examples, shall we? Just so that you get more comfortable with what we've been talking about so far before I move on to other reactions. So let's look at how simple these things should be. So let's start with a molecule like CH3. CH2, CH2OH, and the addition of HI, and a little bit of heat. And they want to know what product is formed from the reaction of these two things. Folks, it should not be very hard. This is at its heart somewhat like a substitution reaction. Let's talk about logistics. Let's talk about organic, shall we? So what we have here is a alcohol group that is attached to an alkyl group, an organic. And this is a polar bond. And this alcohol group is a very good nucleophile that's very hard to get rid of. This is not a very good leaving group. A leaving group means it leaves well. Well, this is going to be kind of hard to kick away just because of how attractive it is. So OH group is on that molecule. We have reacted that alcohol in the presence of an acid. This acid just so happens to be hydroiodic acid in this case, and hydroiodic acid is a polar molecule where hydrogen is partially positive and iodine is partially negative. That partial positive hydrogen and this partial negative oxygen with all of those electrons that are around it make a very good case of let's get together, and we see an attraction that exists. The H goes onto the OH group. It protonates the OH group. This OH group turns into a very good leaving group, and that leaving group is water. So when this leaving group leaves, the iodine, which is the only other nucleophile in the picture, goes on and takes its place. So that means that the product from this reaction here is CH3, CH2, CH2, and now there's an iodine there instead of an OH. And that hydrogen hooks up with that OH group, and away they go happily ever after to make water where oxygen can call all of the shots, and hydrogens can't take up for themselves. Sorry, hydrogen. You knew what you were getting yourself into when you signed up for this. Hope you can take care of yourself. Folks, that's all there is to it. Okay? This is a reaction of an alcohol. Again, very surprising that alcohol reactions exist, just simply due to how nucleophilic the OH group is. But we make it ugly. And we make it ugly through the use of a proton. So, let's review a little bit more before I go on. This group, 1, 2, 3 carbons. This is a propane, right? But that propane, we have to drop the E because this is an OH group, which is alcohol. And it's at number 1, the first carbon in line. So this is a 1-propanol, or just simply propanol. So propanol reacts with hydroiodic acid in order to give us 1-iodo-propane and water. That's how we do it. Let's look at another one. Here, I'm bringing in a ring. This is a molecule that was introduced in Chemistry 251. And that ring with the OH group reacting with an HBr in the presence of some acid. What happens? Well, the same thing. That's what happens. You'll learn the template first, and then you apply it to everything. So what you will end up with is that HBr gives a proton to the solution. The proton goes, protonates the OH group. That protonated alcohol group leaves in the form of water, and bromine goes on to the carbocation that is there. So what we end up with here is a bromine instead of an OH group, and then little o water that goes off on its own yet again. Okay? Let's look at another example, just so you can feel really good about this material before I go on. That's what this is all about, right? Do I understand it? How good do I feel with it? Can I pass it on a test? All right, so there we go. Little bit of heat. Now what? Just like before, there's no difference. We have this molecule. This molecule is a 1, 2, 3, 4. So this is going to be a butanol. This is actually a 2-butanol, carbon 1, carbon 2, carbon 3, carbon 4. So on the second carbon, I have the OH group. And on the second carbon, I have a methyl group as well. So 2-methyl, 2-butanol reacts with hydrobromic acid. And when that happens, we protonate the OH group. That OH group now leaves, because it's a very good leaving group called water, and Br goes on to the place in a substitution type of reaction. So we'll end up with CH3, CH2, carbon, CH3, CH3, and now a bromine that's here instead of an OH group. The other version, or the other product, is also water. How was that? Was that okay with you? If so, you've just learned your first topic in Organic Chemistry 2. See, is that very hard? I don't think it's very hard. It just really depends on how it's explained. And maybe, if you've taken this class before in the past, you had an instructor that probably just gave you all kinds of lingo, proper language, proper definitions to make them all sound smart and fancy. But folks, that's not how I'll operate here. If I break it down to you in layman's terms, if I break it down to you in crazy terms that might make no sense at all when I introduce them in the very beginning, and then you kind of see that relationship and it sticks with you and it helps you remember it, that's all that this class needs to be about, right? That's what this is about. So here we have 3 different examples of our first alcohol reaction. It's a protonation reaction that we have protonated the alcohol group. That alcohol group turns into a leaving group. That leaving group leaves, by definition, making room for the incoming nucleophile that we are bringing in. In the first case, that nucleophile was an iodine. In the second case, it was a bromine. And in the third case, it was a bromine again. All right. So, welcome to Organic Chemistry 2, alcohol reactions. And this is as complicated as it's going to get? Well, now, that I did not say, now did I? I said this was your first encounter of an alcohol reaction. That's what I said. I didn't say this was going to be it, and I didn't say that this was as hard as it was going to get. But we're just now testing the waters. Oh, what does this mean? So before we go on to our next example with the alcohol reactions, there is something that I do want to clear up, just almost like a side note here. So actively thinking about these reactions, what are some of the other possibilities that begin to go on, and why do they not really form, and why do they not happen? Well, notice that when I started off this lecture, I talked about substitutions and eliminations both, right? So let me go ahead and do this example again and talk about maybe a potential side effect that begins to happen. So here we have an alcohol. It's a tertiary alcohol, and we are reacting it with hydrobromic acid. So you're going to look at this and you're going to say, oh, okay, I understand what happens here. This protonates the OH group and pop, off it goes. And that OH group now is going to be replaced by a bromine, and there we go. So that is true. That is a proper answer for this reaction. However, some people might look at this and say, well, wait a minute. When we talked about substitution and when we talked about elimination, we said that if a group, pop, off it goes, this carbon could make the decision to say, well, wait a minute here. Maybe I don't want another group to come in. Maybe I don't need that bromine. Maybe I do not need to share my life with anyone. Maybe I want to be single for a little bit. I don't want that relationship to take place. Well, that would be what we called elimination. Elimination eliminates the group and it doesn't replace it. So the question here that some people do have is, will there be a chance that that bromine will not come on? Because that's substitution. Will there be a chance that this carbon says, no. I've had enough. I don't want another relationship. So I'm going to form a double bond that is here. And there we go. Well, the answer is that, yeah, there is a possibility of this, but you don't have to worry. The reason you don't have to worry is because, look, this is an alkene. If this is what goes on, this is an alkene. And I still have it in the presence of acid. There's still HBr there. There's HBr that hasn't reacted yet. It's still there in the container. It's in the vessel. It's in my beaker. It's in my flask. It's there. And folks, if an elimination product happens, and it could, this is a possibility, the reason that you don't worry about this possibility is because if the elimination happens, that double bond breaks and two sides of attachment open up. Hydrogen goes on one side, and guess what? Bromine goes on the other. And it ends up with the same product that the substitution reaction would have ended up with. So please keep that in mind. So there is a possibility it could eliminate, not substitute. There is a possibility that that double bond would form. However, when it does, that double bond is in presence of an acid, and we go right back to the reactions of alkenes that we did back in the day. The alkene bond breaks, two sides of attachment open up. In this case, H plays with other H's, and the Br goes on to the other carbon. And we end up with the same product that we had before. So do not worry about the elimination products in these alcohol reactions. It's okay, because they're going to be self-destroyed yet again and form the product that the substitution would have given you. Now, if we're talking about substitution, we also need to kind of go back and review something else. First, if we're talking about substitution in terms of SN2, this is where the carbon is a cheater. And it sees two things at one time. And then in the version of SN1, this carbon is not a cheater. And it only sees one thing at one time. That means that this forms a full carbocation. And this does not form a full carbocation. It doesn't have time to. I mean, when one's out the front door, the carbon's sneaking the other one from the back door, and it's seeing both of them at the same time. So there's no chance for that carbon to be single. There's no chance for that carbon to form a what we call a carbocation. In SN1, there is. It sees one thing at one time. So carbon breaks up, carbon single, we call that a carbocation. That single carbocation looks at its life and it says, can I make this any better? Can I rearrange my life? Can I reorder my life in a way that makes it better for me? And if so, then it does. So what we'll see in SN1 is that if it forms a carbocation, we need to pay attention to carbocation rearrangement. That is very important here. Carbocation rearrangement. As far as SN2 goes, SN2 mainly happens with primaries. Again, there's no neighbors around. If so, they're not nosy. So that carbon freely cheats. SN1, you're in a neighborhood that's sandwiched on top of each other in the front and on the sides. And if you're going to be cheating, all the neighbors around you know. Look at you. Oh, you should be ashamed of yourself. One's going out the driveway and the other one's coming up the street at the same time. I mean, at least take a rest in between them. But all your neighbors see what goes in and out of that house. Shame, shame, shame. SN1, well, those are secondary, those are tertiary. No cheating. One goes away. You're single for just a little bit. And then the other one comes in after the fact. All right, so there's a quick review yet again of substitution reactions. Something else that I would like to say before we move on is this idea of primary alcohols. All right, so a primary alcohol is something that we've been using, CH3, CH2, CH2OH, and let's say we react this with HCl. You know, up until this point, I've been putting like the triangle there for heat, and this reaction takes place, and I said the OH goes away and the Cl goes on in its place. Substitution kind of goes on there. So I have propanol. Propanol reacts with hydrochloric acid. Hydrochloric acid protonates the alcohol group. That alcohol group turns into a very good leaving group that we call water. And that leaving group leaves. That frees up a space for carbon to share a bond with something else with. And that is where chlorine goes in for the move. So we do a switcheroo. The problem here, though, is that primaries are a little bit stubborn. We like to use a catalyst here, and that catalyst, its only purpose is to speed up a reaction, and this would be something like zinc chloride. So if you do see zinc chloride here, this is okay. Do not use this in a product. Do not think that it takes part in the product. This is a catalyst, and by definition, a catalyst is only speeding the reaction up so you don't wait forever, right? So don't let that throw you for a loop. If you see that, just understand it's just like heat. It is a catalyst. You're not writing triangles in products, are you? So don't write ZnCl2s in products either. Those are catalysts by definition. They do not take part in the reaction. They only speed them up, and they do not make products with those catalysts. Now, how does that process work? I'm not really interested in those details, okay? The zinc chloride actually associates itself with the OH group. That OH group rips the ZnCl off. Another chlorine goes on to its place, and then we get some rearrangement possibly that happens. I'm not really interested in any of those details because it's not actually generating product. It is just a catalyst, and that is the only thing that it's doing. Okay? All right, so ZnCl2. Don't let it throw you off. They use it very often for primary alcohols, and that's why it's there. Okay, so let's take a look at another one. Let's take a look at CH3, CH, and let's put a CH3 up here on top. And then we'll do maybe CH with an OH group here, and then CH3. And let's add HBr here. We want to know what happens. What goes on? Here we have an organic molecule reacting it with HBr, and we're forming some products. What are those products? That's what the question's going to ask. Let's do some general review. Let's name this sucker first. All right, longest carbon chain. 1, 2, 3, 4. All the way across. Bute. So this is a butane. Well, this is an OH group, so that means this is a butanol for alcohol. Butanol, O-L-O-L. If I'm going to name it as an alcohol, I'm going to number closer to that side. So carbon 1, carbon 2, carbon 3, carbon 4. So this is a 2-butanol. And then on carbon number 3, folks, I have a methyl group. So 3-methyl, 2-butanol. So just like before, just like we've talked about, HBr gets brought in, HBr protonates the alcohol group. That alcohol group decides to leave. So this is what I like to do in these reactions. If you've had me for Chem 251, you kind of anticipate this. You know that it's going to happen. But I always like to start off with my reagent again. When I start generating these products and trying to think about what goes on, I always just like to redraw those. It kind of helps me put everything in perspective. So when the OH group gets protonated from that HBr, right? Here's the H. Well, that's a very good leaving group. Boop, off it goes. So I'm going to erase it. There we go. And that carbon is now a carbocation because this is a secondary carbocation. That's okay with it. That carbocation can form because secondaries undergo a SN1 reaction. And that SN1 reaction sees one thing at one time. So it just got rid of the OH, and now it's on the prowl. It's looking for its next man or its next woman. But in the meantime, this carbon's going to say, before I bring anybody in, I just kind of want to make sure that I see everything else around me, and I kind of evaluate my life and make sure that this makes sense for me. So this carbon, it's now a carbocation, says, here's my chance. I'm going to look right-handed, and I'm going to look at this carbon, and this carbon is a primary primary carbon. It's only attached to one other. And it says, no, that's not better for me. Stability-wise, tertiary is more stable than secondary, which is more stable than primary. So it looks right-handed and it says, oh, whoa, wait, no. Oh, I'm not going back there. I'm not going to primary. My life was much worse off back then. Then it looks left-handed. And it looks at this carbon. And it says, oh, look at here. This carbon is a tertiary carbon. I've got one to the left and one up above and one to the right. That carbon's attached to 3 others. That's where I want to be. So that carbocation shifts. Now, when it shifts, it has to trade places with something, right? I just can't move the positive down and say, there you go, done deal. No, it doesn't work that way. You've got to switch places with something. Well, what that carbon does have is a hydrogen. And those hydrogens, you know, I hate to say it, they get used all the time, folks. They just get tossed around and used and beat up all the time. Poor little hydrogens. So what we'll switch here is the carbocation and the hydrogen. We do a switcheroo dance. All right, so I'm going to erase this positive piece, and I'm going to erase this hydrogen. And that positive now comes here, and that hydrogen now shifts over there. There's the switch. We call this a 1,2 hydride shift. That was something else that was also introduced in Chemistry 251, and it's now coming back. You got to switch with something. You can't just move the carbocation down and around. So now that carbocation feels much better. It says, listen, I have now reordered my carbocation. I've put it into a better place. I now feel a little bit more comfortable in life. Maybe this was a job promotion. Maybe this was moving into a bigger home. Maybe it was getting a nice new fancy car. Whatever it did, it rearranged. Something is now changed than what was there before. And this 1,2 hydride shift allows the molecule to form a more stable carbocation. And now, keep in mind, the bromine is still out there, right? The hydrogen was used to protonate the alcohol and make it leave. That bromine is still out there. At this point is when that carbocation says, okay, come and get it. Here it is. And that bromine swoops in and attaches to that carbon. And folks, there's your product. And this is what we would call the major product of the reaction. The major product of this reaction, I could name it. Longest carbon chain, 1, 2, 3, 4, continuous, so it's still a butane. On carbon number 2, because that's the closest to the bromo group, which is a little bit different, and the methyl group. Put them in alphabetical order. 2 bromo, 2 methyl, butane. There it is. That is what we call the major product of the reaction. Now, why do I say major? Well, let's go back. Let's rewind it a little bit, okay? So here is this molecule all over again, but before I shifted it. There is a chance that this carbon might be blindsided a little bit. You know, the carbon's anticipation here is I am going to rearrange. I see this tertiary carbon over to, I see this tertiary carbon over to the side, to the left-hand side of me. And because of that, I'm going to shift my carbocation, but it stops dead in its track. And the reason is because that bromine might actually beat it out before it gets there, depending on how much bromine's there. So that is a possibility. You know, that does exist, that does form. This is, again, one of the reasons that organic is not a great science as far as percent yields go, because these are 2 different molecules, 2 different types of properties that are associated with them. My percent yields will rarely be 100% because I'm not forming 100% of one product. It's going to be a mixture almost every single time. And here's one of those cases of why. So because that does happen, we're going to call this a minor product. It happens, it forms, it might be a low amount. It might be like a 70-30 split. It might be an 80-20 split. It could be a 90-10 split. It could be maybe a 60-40 split. But it's still labeled as a minor product for that reason. So carbocation will form. Carbocation will shift. It does go to a new place if it can find a new place to go to. And that is where the incoming group decides to go in this reaction. All right, so now let's take a look at some examples. Show how 1 butanol can be converted into the following compounds. Oh, gosh. What on earth do they want me to do here? They want me to start with 1 butanol. Okay, so there's the starting place. So let's tackle this question little bit by little bit. 1 butanol. All right, CH3, CH2, CH2, but is 4, and then the ol is alcohol. So there is 1 butanol. And it wants me to make this structure for part A. CH3, CH2, 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 O, CH3. And it wants to know, how do you get there? What do you add to that alcohol group in order to make what is down below? And now you're looking at me and saying, what? We really didn't do any of these types of examples yet. What are you talking about? The only thing that we've dabbled in has been HCl's and HBr's. What on earth? Okay, folks, this is what they want you to do. It's a little bit deceiving. And if you missed out on substitution, I hate it for you. Blame your other instructor. Tell them you want a refund. If you've never seen substitution before and you've taken a chemistry 251 class, you better ask for a refund of that tuition money. And this is why. Again, I'm making assumptions. We've completed 251 at this point. There's things that I assume that you know at this point. I've always told my people that organic is a foundational science. You got to lay the foundation, and then you build up on top of that foundation as we go further and further and further into the course or courses. And here's that example. So what we do first is that we add something like HBr or HCl. So that is something that we've talked about. When we do that, the HBr protonates the alcohol group that leaves in form of water, and Br goes on instead. So this is a primary alcohol. We want to probably include ZnCl2 and a little bit of heat. So we end up with CH3, CH2, 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 and then Br. But we're not yet done. The reason is because that is not the product that we need to end up with. So folks, there is another step that's here. What is that other step? This other step is a substitution reaction. Because now we have an ugly old bromine, and that ugly old bromine is a very good leaving group if something else prettier comes into the bar. And what is that pretty group, that pretty nucleophile group that came in? Well, look at your product. This is what you want to add on, isn't it? So use that as the nucleophile. It's as simple as that sometimes. There you go. Look at there. So if we take these two and react them together, now we're pulling back chemistry 251 topics. And this is a substitution reaction. You don't have to write this on the arrow. I'm just doing kind of a quick review here. It's a substitution reaction. It's a nucleophilic substitution reaction because we're using a nucleophile, which carries a negative charge. And what kind of SN do we have? Well, this is primary. Primaries don't have a lot of neighbors around that carbon, just one other. So it's very easy for carbon to cheat. It needs to cheat because it's too unstable to be by himself. So this is going to be an SN2 reaction. And what we see is that the beautiful OCH3 comes into the bar and says, hello. And that carbon looks at it and says, bromine, you got to go. Bye-bye. And then off it goes to pair up with the OCH3. There you go. That's how we make the product from part A. Now, it doesn't tell me to do this, but I do want to do it. Here's the HBr. Here are the electrons on the oxygen. And I want to talk about mechanism. Right? We need to kind of talk a little bit scientific here. These free pairs of electrons, folks, these are negative. This is where my arrow is going to start. And the first part of that mechanism leaves those negatives and it goes to that hydrogen. It's going to pluck that hydrogen off. And this is how it forms the protonated alcohol group, aka water. And the bromine takes those electrons from the bond and it leaves. It's electronegative. It wanted them anyway. And this is kind of the step of how that forms. Now, what we're leaving off here is the protonated alcohol group. So eventually, an arrow would be drawn to the OHH, and away it goes. Then the bromine would have an arrow that points to that particular carbon. That's how we ended up with CH3, CH2, CH2, CH2Br. Now, in this step, we can talk about mechanism as well. This is a negative area. That's where my arrow is going to start. This mechanism makes that negative go to that partial positive carbon. That carbon says, oh no, I can't see more than 2 people at a time. What are you talking about? And it says, bromine, you got to go. So the bromine takes those electrons and it leaves. So a little bit of insight about mechanism review. That's the only reason that I did that. And there's kind of a brief memory jog of what Chem 251 should have shown you a little bit of. All right, so in the next video, I want you to kind of see if you can dust off the filing cabinet, bring out some of those things that we've talked about in the past, or in a Chemistry 251 class, and look at part B, C, and D. Jot these down. How do you form those products? Can you tell me how we form those products? And then push play on the next video and come back and double check your answers. You know alcohol is going to be involved. You know protonation is probably going to be involved. Then after that, it's kind of up to you. What do you think is going to happen here? All right, so good luck. Answer B, C, and D. Take a stab at it. If you get the questions wrong, I have no clue. I can't see you through your computer screen, or can I? And then press play and check your answers. I'll be here when you're ready.